Welcome back, everyone, to your favorite YouTube channel, Complanner Studies, where we look at difficult things in science, technology, engineering, mathematics, just those things you find difficult to understand. We make them simple here. In this video, we'll be continuing with our Calculus 1 series, and this is lesson 3, actually. We're looking at left and right limits. So we're going to have two parts here, part 1 and part 2. But in this video, we'll be looking at part 1 of left and right limits. So left and right limits, part 1, let's dive into it. So, well, I'm just going to solve examples on left and right limits here. I think 4 examples is enough for this video. So, first of all, I'll give you some background knowledge on left and right limits. So, when we say evaluate the limits at the left, okay, you know what? Let me just let's visualize it on a piece of paper. So, when we talk of evaluating limits from the left, so left hand limits. So in a left hand limit, you're evaluating the limit of a function as you approach a specified value from the left hand side of the graph. That may sound confusing at first, but give me some time to explain this to you. So we have, it's written in this form: limit as x approaches any value, actually, let's say 1, x approaches 1 minus. So this minus sign here means from the left. So minus means left hand limit. And if you see plus, like a power plus, it's just going to be a power to the value, the specified value. So plus means right hand limit. So limit as x approaches 1 from the left of f of x. So this means what is the limit? What is the value of the limit of f of x as we approach left? Now let's have a picture. Let's visualize this using a graph. Now let's look at the function x squared, right? F of x is equal to x squared. If I ask you for the limit of this function x squared as x approaches 1 from the left, what will the answer be? So I'm going to show you how to solve this in this video, how you can solve something like this in this video. But let's have a picture of what we mean by left hand limit using a graph. So we have our graph space, and I'm going to enter in the function. And okay, so there's our function x squared. If we zoom in, we see that as we approach 1, this is 1, as I'm approaching 1 from the left. So I can approach 1 from two sides on this graph. I can either approach from the right, from here. I'm approaching from here. I can approach from, so your right is not my right and my left is not your left, it's opposite. But then I think we can both see that this is the right hand side of the graph, and we are approaching 1 from the right. We are approaching 1. We see that the values of f of x, that is the values that you see on the right of the brackets there, those two brackets we have, because we have two brackets. Okay, we have two brackets. So we have two values in the bracket, x comma y. So the one that's here, over here, this is the one we're looking at. This is the values of f of x. This is f of x here. This one. So the ones at this side is what we're really focusing on, while this one is the x value. This part will be approaching 1. So look how this part should be approaching 1. And then we want to find out what this is. So take note of that. So let's get back to our simulation, our graph. Now, as we are approaching one, this is approaching one from the right, but that's not what we are asked. We are asked for the left. So we approach one from the left, and we see that we have 0.87, 0.88, 0.9. We are approaching one. We see that the values of y, right now I have a value of x at 0.949 and a value of f of x or y at 0.900, and I keep on approaching from the left. I keep on approaching. So I see that as I keep on approaching one, right now my value of x is 0.988. That's very close to 1, right? And my value of f of x is 0.9761400. So I'm seeing that I'm approaching 1. I'm approaching an f of x value of 1 as I approach 1 on the x-axis from the left. I'm approaching from the left. I'm approaching 1 from the left, and my values of f of x are approaching 1. So that's the concept of a one-sided limit. You're only approaching 1 from one side. You're not looking at both sides now. In our previous video, we were actually looking at both sides. Okay, approach from the right and the left, and if you get the same thing, the same value, then yes, you can then conclude that the limit of this function is this value. But in this one, we are only approaching from one side. So that gives us the basic concept of what we are doing. So let's jump right back into the slides. So we have our first example. It asks us to evaluate this limit of x squared minus 1 divided by x minus 1. This is the function. And look, as x approaches 1 from the right, plus right. So we know what we are asked in this. We are asked as this approaches 1 from the, as we approach 1 from the right. So we'll just get right into that. Limit as x approaches 1 from the right of x squared minus 1 divided by x minus 1. Okay, so this is what we have. Now, the first step in doing this is to, as usual, simplify. So how do we simplify? Now, in our previous videos, what we normally do is that we test, right? We just substitute 1 inside. We substitute 1 inside, and then we see what we'll get. If we get the indeterminate form 0 over 0, then we now know that, okay, we need to apply another means, another way to solve this. But since this is left and right limits, it's advisable that you simplify first. Try and see if you can simplify. You should be able to see if something can cancel out something. If I can simplify something here, and if you remember what I said about difference of two squares, where you have a squared minus b squared, and you want to factorize this. You want to factorize it. This gives you a minus b multiplied by a plus b. Okay, so now I've seen x squared here minus, minus 1. Is 1 a squared? Yes, it is. 1 squared, right? 1 squared is still equal to 1. So 1 is a perfect square. And even if it wasn't a perfect squared anyway, let's say it was x squared minus 7. Let's say we had x squared minus 7. So let me put it here. X squared minus 7. I can still express this as x minus the square root of 7 multiplied by x plus the square root of 7. Now, the thing is that the square root of 7 squared, let me write it here, the square root of 7 all squared is equal to 7. So even if the number isn't a perfect square, I can still get a difference of 2 squares, because I know that I can express it as x minus the square root of that number. You get that. So Once I see x squared minus anything, I can easily express it as a difference of two squares, difference of two squares, and then factorize it using that method. So here we don't need square root because 1 squared is 1. So this can actually be simplified into the limit as x approaches 1 from the right of x minus 1 x plus 1 divided by x minus 1. So the x minus 1 from the denominator is still there. I've expressed the numerator as a difference of two squares. Now it's very obvious at this stage that this can cancel this. We've seen that, so we just knock them off and we are left with this limit as x approaches 1 from the right of x plus 1. Now this is where the actual solving or the actual reasoning comes in. We have x plus 1, we have x approaching 1 from the right. So you have to have a mental picture in your head. Okay, I have x plus 1. What kind of graph am I expecting actually from x plus 1? Let's look at that. What kind of graph am I expecting? X plus 1. It's a straight line, okay? It's a straight line, just go straight like that. And we are approaching 1 from the right. We are approaching 1 from the right. So as I approach 1 from the right, as I'm approaching 1 from the right in x plus 1, I am going to approach the value of x at 1. Of x plus 1 at 1, not of x at 1, of x plus 1 at 1. So as I'm approaching 1 from the, okay, x plus 1 is 2, right? X plus 1 at 1, that's 1 plus 1, it's 2. So I'm approaching 2. I can see it here clearly at 1.1 1, I have a y value of 2.132. I'm approaching 2. So as I approach from the right, I keep on approaching to look at that 1.004 at 1.004. That's close to 1. X value of 2.004. So it therefore means that we can just put 1 here where we have 1, where we have x here, because we know that as we approach 1, as we are approaching 1 from the right hand side, we are still approaching 1. So we have 1 plus 1, which gives us 2, and there's an answer. Now this is a very simple basic right hand limit. You actually encounter things a little bit more complex than this, but I want to start with this one first, because let's start easy and then go to more complex, harder stuff. And speaking of complex and slightly harder stuff, we have example 2 here. In this one, we are evaluating the limit of the, now I know what's going through your mind. What are these? What kind of bracket is this with it's not like the normal parenthesis, the normal curved brackets that we have. It's 2 slashes. So to answer that question, these mean absolute value. This is the absolute value function. So very brief on the absolute value function. Let's just look at it very briefly on what the absolute value function does. So the absolute value function, or the absolute value command, just trying to make it in simple terms here. When I say absolute value of -1, the answer is 1. When I say absolute value of 1, the answer is 1. So what the absolute value does is that it makes all non-negative, it makes all negative non-zero numbers positive. In simple terms, you can say it makes everything positive, but yeah, like absolute value of 0 now is still 0. So uh well, you only get positive numbers from the absolute value function in general. You always get positive numbers. So if your number had a minus sign, just dump the minus sign. I think that's the most basic explanation here. Dump the minus sign. Dump the minus sign. And you just write the number there. It can also be seen as the magnitude of the number in such terms. Magnitude of the number. So now that we have an idea of what we are looking at, we can better understand what we are being given, what we are being given here. Absolute value of x squared minus 4 divided by x minus 2. And we're asked to evaluate the limit of this function as x approaches 2 from the left. Now, a word of advice here is that whenever you see absolute value of anything, you've got to like switch on your awareness. You've got to be alert. Okay, there's an absolute value here, because as we are going to see shortly, the absolute value has a sort of thing that it does to a function. Your left hand limit will not be the same as your right hand limit in cases like that. That's what the absolute value does. So you have to reason. You have to reason through, and I'm going to show you how to reason through stuff like this. So let's attack this. We have the limit as x approaches 2 from the left, absolute value of x squared minus 4 divided by x minus 2. Now we begin solving. So the first step we're going to take here is to consider the absolute value. That is the first step we take. And in this absolute value, we have x squared minus 4. X squared minus 4. Now, we are going to simplify what we have in the absolute value function. Simplify this. So we have limit as x approaches 2 from the left of, now this is the difference of two squares, right? X minus 2x plus 2. Difference of two squares, x squared minus 4. 4 is a perfect square, so yeah. Now, this is where most people get it wrong. This is where most people get it wrong, because they'll just go ahead and use the x minus 2 here to knock off the x minus 2 here, and then say, yeah, they're the same, right? So they knock off. Now, hold on. We know that they are the same, but then, would they have the same signs? Because it's one thing. Okay, you have 1 divided by minus 1. Okay, you can say, okay, 1 knocks off 1 here, and the answer is 1 is completely wrong. Why? Because you didn't take note of the minus sign here. The answer is actually minus 1. So what we do is that we consider the brackets here, the absolute value. Sorry, we consider the absolute value. We have absolute value of this. Okay, so after that, we look at how we approach 2. We approach 2 from the left. Now, this is where your ability to picture the function comes in. So, okay, sorry about that. You can actually look at this as, we can further break it down as absolute value of x minus 2 multiplied by absolute value of x plus 2 divided by x minus 2. You can actually do that. Yeah, this is actually equal to the absolute value of this one multiplied by the absolute value of this one. That's how the absolute value works. You can break it down, although it's not okay. Yes, okay, it's kind of necessary because we're about to cancel out something, so you can actually break it down like that. And now back to what I was saying. You consider how you approach 2. That's how you reason. How am I approaching 2? I'm approaching 2 from the left. Now I'm looking at x minus 2, and I'm approaching 2 from the left. What's going to happen? Let's pick a number that's at the left of 2. Numbers at the left of 2 are, if we look at a graph, typical graph, The numbers we find at the left of 2 are numbers like 1, 0, minus 1. So we can use them to test, right? We can use these numbers and test. So x minus 2, if I put in minus 1 at the point I have x, if I'm up to put minus 1, I have minus 1, minus 2, giving me minus 3. So this is negative. This is negative, right? So it means that the answer I'm going to get from this is going to be negative for all numbers less than 2, because any number to the left of 2 is less than 2. And now you're taking a number that's less than 2 and subtracting 2 from it. So of course, a number that's less than 2 is not big enough for you to have a positive result. Any number less than 2, when you do that number minus 2, you're going to have a negative number. Even if it's even if it's 1.9, for instance, you'll get minus 0.1. It's still negative. So any number to the left of 2, which is less than 2, all numbers to the left of 2 are less than 2. We can see that on a typical graph, like 1 is less than 2, 0 is less than 2, minus 1 is less than 2. All numbers to the left, because we're approaching from the left, so definitely we're using numbers from the left to approach 2. So I'm taking my time to explain this because people get it wrong here a lot, so you have to take time to explain this. So I approach from the left of 2 and I'll be getting negative numbers. So it therefore means that x minus 2 is negative. We'll be giving negative results as we approach 2. Now, what the absolute value here does is that it nullifies that negative and makes it positive. So you'll be receiving positive results, positive x minus 2. Positive, like here now, it's going to turn this minus 3 to 3. Absolute value of minus 3 is equal to 3. So it's going to turn this to 3. But then for the denominator, it does not affect the denominator. The denominator here still retains these negative results. Okay, it still retains the negative results. So you can have a picture here of x minus 2 being negative for the denominator and x minus 2 being positive for the numerator. X minus 2 negative for denominator, x minus 2 positive for numerator. So here's what we're going to do. Now, what I have in front of, what I've done here is that I had to skip because I was trying to copy our previous results here, but I'm going to explain what this whole line means. Now, it's basically the same as the previous one, but just that if you notice, I've removed the absolute value from x minus 2, okay, but there's still an absolute value on x plus 2, multiplied, dots here for multiplication. And I've attached a negative sign to x minus 2. Now the answer, the question is why? I've attached a negative sign here because this is positive. We've seen that this is going to be positive. Okay, to start first, let's start first with x minus 2. We saw that x minus 2 is going to be negative as we approach 2 from the left, because you're using numbers that are less than 2 to approach 2. So that means that x minus 2 is going to be negative results. X minus 2 is going to be negative as you approach 2 from the left, and the absolute value makes that positive. It makes it positive, the absolute value, but then on the denominator it's still negative. Okay, so I've attached a negative sign to the denominator and I've removed the absolute value from here. So it's essentially what I'm saying is that they have opposite signs. That's the thing. They have opposite signs as you approach 2 from the left. The numerator is going to be positive. X minus 2 is positive because of the absolute value. And the denominator is still going to be negative as you approach 2 from the left. So they have opposite signs. Now I can cancel. And as I cancel, I take note of the negative sign here. So what do I have? I have the limit as x approaches 2 from the left of this means this divided by, okay, let's go gradually, x plus 2 divided by negative 1. By the way, constants can actually come out of a limit. Like you can, if you have a constant multiplying a limit, like here, we have this divided by minus 1, which is the same thing as the limit as x approaches 2 from the left of minus 1 multiplied by x, absolute value of x plus 2. This divided by minus 1 is the same thing as minus 1 multiplied by the numerator. It's the same thing. So the constants can actually come out of the limit. You can do that. So in this case, minus 1 multiplied by, you can only do this when the constant is multiplying everything. If it was minus 1 multiplied by absolute value of x plus 2 plus 5, then I can't really like remove minus 1, because it's not multiplying, it only covers the x plus 2, not the 5. So, but in this case, it covers everything, the entire limit, what we are evaluating, so it can come out. And in the bracket, I have absolute value of x plus 2 left. So now when I put in, when I come again and I approach 2 from the left, so you have to have this reasoning of I'm approaching 2, but I'm approaching 2 from the left. So I'm approaching 2 from the left, that means I'm using numbers that are less than 2, like 1 for instance. If I have 1 plus 2, it's x plus 2, so 1 is less than 2, 1 plus 2 is 3. So any number that's less than 2 plus 2 would always be positive, right? Like, okay, minus 100, minus 100 plus 2. Okay, no, sorry about that. The thing is that why is it numbers less than 2 to add to 2? So as we are approaching 2 from the left, we see that our answer is just good. Our answer for what's inside here is just going to be x plus 2. As in, if it's 1, it's going to be 1 plus 2. Minus 100 plus 2 is minus 98. So this is x plus 2. The absolute value here changes that. The absolute value is going to change this to positive. So we're going to put in 2 where we have x here, just straightforward. Minus 1 multiplied by the limit as x approaches 2 from the left. Okay, sorry, this is, since we're evaluating the limit now, so there's no need for that. Minus 1 multiplied by the absolute value of 2 plus 2. So I've put in 2 there where I have x. So absolute value of this is equal to minus 1 multiplied by absolute value of 4, which is equal to minus 4. So this is the answer for that question, minus 4. So as we solve more problems, we'll get used to this method. Let's move to another example. Okay, but before that, we can just visualize this on the graph. Now, this is the graph in front of us, the graph of the function where we find the limit of absolute value of x squared minus 4 divided by x minus 2. And as we are approaching 2 from the left, we keep on getting values that are closer to minus 4. We keep on getting values closer and closer to minus 4, which is our answer. So as we are approaching 2, this is 2 here on the x-axis, from the left hand side, we see values that are close to minus 4. So here we have 1.999999. We have minus 4.0000001, something like that. So we'll just stop there for now. Let's move on to the next example. Okay, so example 3 is the same problem, but just this time around it's from the right. So I want to show us something here. That's why I'm solving the same problem 2 times, but just with different one-sided limits, because there's something I want to show us. So very quickly we'll be solving the same problem, but this time around it will be from the right. This time around it's going to be from the right. So yes, from the right this time around. And let's solve. This time will be faster because we already have all the ideas of what to do. So solving, we have limit as x approaches 2 from the right of, we can break this down to x minus 2x plus 2, absolute value of that divided by x minus 2. We all know what happens from the previous example. We know that we can break this down. Okay, absolute value of the first one multiplied by absolute value of the second one. When you have a multiplication holding the two terms in the absolute value together, you can break it down. Absolute value of this term multiplied by absolute value of the other term. It's okay to do that, divided by x minus 2. Now, as usual, we do some testing. We cannot go ahead and just say, okay, this cancels this, because this has an absolute value and this does not. So we can't cancel them. If they both had an absolute value, however, then yes, we can go ahead and cancel. But since this one has an absolute value and this one does not have an absolute value, we cannot cancel. What we can do instead is to look at what happens, look at the limits, the side we're approaching from, and evaluate what's going to happen if we approach x in that way. So we're approaching from the right, meaning that we are approaching from here. We're approaching from the right. So we're passing numbers like 6, 4, 2.5, 2.3, 2.1. These numbers are greater than 2. These numbers are greater than 2. And when we use any number that's greater than 2, and we subtract 2 from it, then we're going to have a positive number, right? Like 3 minus 2, for instance, is 1. 2.1 minus 2. When you have 2.1 minus 2, that's still 0.1, which is still positive. So you have a positive number. So we're getting a positive number from here, the denominator. Now for the numerator that has the absolute value here, the absolute value of 0.1 is still 0.1, right? Yeah, so it doesn't change anything. So we can say that they are the same in this scenario because they have the same sign. Unlike the previous example that the denominator will be negative and here will be positive. So we had to attach a negative sign to the denominator and then cancel out. So in this case, we are not attaching any negative sign because we see that we have the same sign. We have the same signs. This is positive. What's inside is positive. X minus 2 is positive as you approach 2 from the right, and absolute value of that positive answer gives you a positive answer. So they are practically the same. They are the same. So we go ahead and write it like this: x minus 2 absolute value of x plus 2 divided by x minus 2, and we can cancel out. We don't need to attach a negative sign in this case. Cancel those out. So we have the limit as x approaches 2 from the right of the absolute value of x plus 2, and we approach, as we approach 2 in x plus 2, as we are approaching 2, we have a absolute value of 2 plus 2, which gives us absolute value of 4, which gives us 4 as our answer. Now this is the opposite. This answer is opposite in sign to the answer we got from the previous example where we had a minus 4 We had a -4 from the previous one, but here we are having a +4. So now this is very interesting because as you approach the same number 2 from both the left, and from the right, you get different answers. The same answer but different sign. Now the thing is, how is that possible? How is that possible? So let's go back to the graph so I can show us something. If I zoom out, you'll see that this graph has actually broken. I don't know if you've come across a graph like this, but this is a type of graph that has a jump. We call this kind of thing a jump. It has a jump at -2. This jump occurs because it has two different limits, two different one-sided limits. Now I'm going to say a lot of things. Just pay attention to what I say. So this is a jump. It's like someone broke this graph into two and just kept one at the top and the other at the bottom. But all jokes aside, what we have here is a limit that does not exist. Now, if I were to now ask you a question, okay, from what you've seen, what is the limit? What is the limit as x approaches 2 of the absolute value of x squared minus 4 divided by x minus 2? This does not exist. In calculus, we typically write d and e. Does not exist. Why doesn't this exist? It doesn't exist because this function has two different one-sided limits. So we look at the graph of the function and we see something. We see that we have two different one-sided limits, as I said. I mean, the limit as you approach 2 from the left-hand side is -4, and as you approach 2 from the right-hand side, it's 4. So 4 minus 4. So this limit does not exist because you're having two different values. So a limit cannot exist if you have two different values. When you approach a specified value from the left and right, you're getting two values. The limit does not exist. You must approach the same value, the same f of x, the same y value as you approach the specified value from either the left or the right. You must approach the same value for a limit to actually exist. And if you don't approach the same value, if you don't approach a particular specified value, then the limit does not exist. So that's the concept there. This limit does not exist. There is no such thing as the limit of this function, the one we were using. It doesn't have a limit at 2 because it has it has a different right limit and a different left limit. They're not equal to each other. So that's the concept there. So we can move on to our last example for this video, which asks us to evaluate the limit of 1 over x as x approaches 0 from the minus sign here means left. So we know what we are dealing with. So let's get right into that. I've already done this beforehand, so I'm just going to explain the process. So we have this limit. The limit as x approaches 0 from the left of 1 over x. Now, the thing is, you ask yourself the question, as I approach 0 from the left, what happens? So we are approaching 0 from the left, right? Meaning that we are using numbers that are less than 0. We are coming from the left. Look at the cursor. We come from the left and we approach 0, meaning that we are using numbers that are less than 0. That is, we're using negative numbers here, numbers with negative signs, to approach 0. Now, minus 2 is less than 0. 1 over minus 2 is the same as negative 1 over 2. You have a negative value there, a negative value. Now, what if we try minus 0.1? Minus 0.1 is to the left of 0. It's less than 0. And when we compute 1 over minus 0.1, we get minus 10. Okay? Let's try a number even more close to 0. About this. A number even more close to 0, minus 0.01. We get minus 100. 1 over minus 0.01 is minus 100. Minus 100 is less than minus 10, but it has a higher magnitude, as in the magnitude increase. 100 last time was 10, now it's 100, but we have a negative sign. Okay, so now it's minus 100. If we try minus 0.0001, we'll get minus 10,000. Okay, so we keep on getting, should I use the word bigger in quotes, although they are lesser numbers, we keep on getting smaller numbers on the y-axis, but their magnitudes are bigger than the previous one, but they are negative numbers. So you'll keep on getting numbers like minus a million. As so far as you keep on approaching 0 from the left, you get negative values that have bigger magnitudes. So we use that. We just take note of that. That's a concept that we should just hold on to. Now, another concept is that when you have 1 divided by 0, this is seen as a very large number. It's infinite. Okay, it's undefined, but then it can be seen as what's the word I'm looking for? The limit as you approach the limit of 1 over x as you approach 0 from the right. I think from the right, as you're approaching 0, you get big numbers. Like, for instance, 1 over 0.01 would give you 100. 1 over 0.00001, which is a number that's extreme, that I won't say extremely, but it's close to 1. I mean, it's there. You get I end up getting, I think, 100,000. Yeah, 100,000 from that. So you keep on getting big numbers as you approach 0. So now, if I attach a negative sign to this number now, it alters this result to negative, right? Negative. So as I can now conclude that as I approach 0 from the left hand side, I'll be getting very large in magnitude, very big negative numbers. Let me, in quotes, just for the sake of understanding, very big negative numbers in quotes. So minus 1 million, for instance, I keep on approaching 0. So now what do we write? We write negative infinity. This is the answer for this limit, negative infinity. We'll be handling more on things on infinity in later videos on this series. But what I want to say is that you keep on getting very large negative values. So finally, to get a picture of what we mean, what we are discussing, let's take a look at the graph of 1 over x and graph. So we look at this graph and it just shows us what we've been talking about all this time. As I approach 0 from the right, I get I get a lot of large numbers. Look at how the graph just ramps up as I approach 0. It just catapults, you just go up, and then you keep on getting these numbers that are so large. So as if we want to follow the graph, we see that the graph tries to approach the y-axis, but it will never reach there. Believe me, I've tried to see the end, and you just never get to the point where they both meet. And even if it appears as if they have met, just zoom in and you'd see that you haven't even even started. I mean, zooming in, you can still see that there's still some space. So they never meet. They never meet. So this is called a vertical asymptote. More on this in a later video, discussing about vertical and horizontal asymptotes. So for the left hand limit, as we approach zero from the left, as we approach zero, we see that the graph ramps again, but this time it takes a dip, it dips and it goes down really fast as you approach zero, goes down really fast, and you see it going down. It never meets the y-axis. It will keep on going down, down, and down, and down. You can zoom in to see that it doesn't reach the y-axis. So you keep on getting larger and larger negative values. Right now at minus 0.051, I have a y value of minus 19.608. So you get larger and larger negative values. Now, if I were to ask you, what is the limit? If I were to ask you for the limit of this graph here that we have on our hands, as you approach zero, so let's put that in writing. If I were to ask you, okay, what is the limit as x approaches zero? Here, that's talking about left and right limit. Not about the exact limit, not left limit, not right limit, but just the exact limit of 1 over x. This does not exist because you have it approaches a very large negative. It approaches a very large in magnitude, negative numbers as you approach from the left, and very large numbers as you approach from the right. So you have, it does not approach an exact value like the other graphs we've been looking at in previous videos. It doesn't go to an exact pinpoint value. So it doesn't exist. Period. It doesn't exist. You have no definite answer to that one. It just doesn't exist. So from all what we've seen, we now have the concept of left and right limits. We'll go deeper in part 2, but we have the general concept, and we've seen how to take left and right limits. So we've come to the end of this video. I'd like to encourage you to like the video, share the link, subscribe to the channel so that you keep on getting informed if we post any new video. Just get the word out, tell your friends about this amazing channel that breaks down complex or seemingly complex mathematical concepts in very easy to grasp chunks of information that you can relate to. And it's been an amazing video. We've come to the end of this one, and just watch the next one, watch the part 2 to get the full download of this subject. And we come to the end of this video. Have a nice day.